Let's talk about the aromaticity and basicity of pyrrole, furan, thiophene, and pyridine. First of all, pyrrole. You remember that pyrrole is a 5-membered ring compound with 1 nitrogen. Furan and thiophene are analogues of this. If we look at the molecular orbitals of pyrrole, we have 1 electron each for the 4 carbons involved in the 2 double bonds, and then to obtain a 4n pi plus 2 arrangement, the nitrogen in the ring contributes 2 electrons in a p orbital, and that leaves only 2 p orbitals and 1 s, so the nitrogen has to be sp2 hybridized. 1 electron in each hybrid lobe, and one of those electrons shares an electron with the substituent on the nitrogen. In pyrrole itself, that's a hydrogen. And the other 2 lobes, 1 electron each, share with the carbons right and left. Every aromatic system effectively has to have sp2 hybridized atoms, either heteroatoms or carbon atoms, but all sp2 hybridized to give p orbitals connecting around the circumference of the ring. Furan is very similar. The oxygen in furan has to be sp2 hybridized with a lone pair in the p orbital. That leaves 1 electron each to share with the carbons either side, and 2 electrons, a lone pair, sticking out in the same plane as the ring. Thiophene has just the same electronic arrangement. 2 electrons in a p orbital, 2 electrons, lone pair in an sp2 hybrid lobe. 1 electron either side to share with carbons. 4n plus 2, aromatic. Thiophene and furan are aromatic systems. Well, how is pyridine different? Well, pyridine, of course, is a 6-membered ring compound. So if the 5 carbons each bring with them 1 electron in 1 p orbital around the aromatic ring, the pyridine nitrogen only has to leave 1 electron in its p orbital. That leaves 4 more electrons to place, 1 either side to bind with the carbons, and 2 left in a lone pair in the plane of the ring. Here is a classic question for introductory organic chemistry. Compare the basicity of pyridine with pyrrole. Well, first of all, pyridine. What happens when we protonate pyridine? We say we get a pyridinium ion. The proton adds to the nitrogen, and therefore the nitrogen has positive charge. Adding that proton simply adds it to the lone pair in the plane of the heterocyclic ring. But the other 6 p orbitals containing 6 electrons are unaffected. Protonation of pyridine does not affect its aromaticity. So when we protonate pyridine to get a pyridinium ion, then we measure the acidity of that by the pKa. The higher the pKa, the more the pyridine is bonding to the hydrogen. The lower the pKa, the more the hydrogen is free to dissociate. If you don't remember pKa's, let me give you a little reminder from one of my previous videos. Very short summary. Ka is nothing special. It's just an equilibrium constant, gives you the concentration of acid in solution. For organic molecules, Ka's are likely to be small. But if we get into the really bad acids, methane is one of the worst I can think of. Ka is 10 to the minus 60. Now, I can't picture 10 to the minus 60. That's such a very, very small number. And we need some way of keeping it on the same scale. And we do that, of course, with logs. So we take the log of the Ka, Okay, so if you take logs of Kas, this contracts the scale. When you start talking about differences in 10, for the concentration difference, every one difference in log Ka. But then if you're taking logs of small numbers like 10 to the minus 5, everything will be negative, and that's for most organic compounds. So let's flip it again and say minus the log, pKa, and then the numbers turn out to be positive. Now, if you search on the web, you might find protonation of pyrrole shown as a pyrrolium ion. And the pyrrolium ion has a very low pKa compared with pyridine. Let's look at the orbital diagram for pyrrole. If we protonate pyrrole on the nitrogen, we have to use the lone pair on the nitrogen to bond to the proton. Problem. That lone pair is busy giving us aromaticity in the pyrrole. So if it happens, too bad. We'll lose our 4n plus 2 arrangement. We'll go down to 4n pi electrons, not an aromatic system, and we don't get the continuous arrangement of p orbitals around the heterocycle. That will cost energy if pyrrole is protonated. Taking the nitrogen from sp2 to sp3 and disrupting the aromaticity will cost energy. I don't believe it. I don't believe it because pyrrole, furan, and thiophene protonate on carbon and not on the heteroatom. And when they do, they tend to polymerize very quickly. The pyrrolium ion is not a prevalent form in the protonation of pyrrole. Here's a classic question then. Compare the basicity of pyridine and pyrrole. You show the protonation of pyridine, giving a pyridinium ion. The protonation of pyrrole occurs at C3. The nitrogen is 1, the carbon next to it is 2, the next carbon is C3. Protonation of pyridine does not disrupt the aromaticity. Protonation of pyrrole does, either on the nitrogen, which I don't believe, or on the carbon. Here's another good question for introductory organic chemistry. Compare the basicity of pyrrole with a very similar enamine. After all, you could circle an enamine fragment in pyrrole. What's going to be the most basic? Well, protonation of the enamine also occurs on C3. There's no aromaticity there to disrupt, so there's no energy expenditure for doing that. Whereas with pyrrole, when a proton adds to C3, it costs aromatic energy. The enamine is therefore more basic at C3 than the pyrrole is. Enamines are, incidentally, better nucleophiles for alkylation than pyrrole, although both add electrophiles at C3. I really hope that helps with your studies. Thank you very much for listening. Bye-bye.